The last chapter now, so you guys have got to stay up on this stuff. Sorry I'm not here today. I had to take my daughter to her college, so sorry about that. So here's what we're going to do. I need you, one, stop the video right now. Do problems 1 and 2. That's from yesterday. Make sure that you understand it. Turn the video back on once you got them done, and then we'll continue. So stop the video. Okay, welcome back. So we are going to be doing some review on some of our independent things. So suppose Mo picks a number from 1 to 4, and Larry picks a number from 5 to 7, and Curly picks a number from 8 or 9. How many different sets of numbers are possible? So let's just talk about Mo. Mo is picking one number, so this is Mo. And since Mo has choice 1, 2, 3, or 4, he has 4 choices. Got it. So then we go on to Larry. And Larry has the numbers 5, 6, 7 to choose from. So Larry has 3 choices. And finally, we go on to Curly. Okay, did you guys get it? Mo, Larry, and Curly. I hope so. 3 Stooges. And Curly only has 8 or 9 to pick from, so he had 2 choices. So how are we going to figure that out? We multiply 4 times 3 times 2, and I think that you're going to find that there are 24 different possibilities. Okay, these were independent. Just to make sure that you guys hear me say that again. Okay, so now on to the next example. A catering company provides 7-course dinner for a party. Unfortunately, they forgot to label the containers of food, so the courses have to be served in random. How many different orders could be served? So there's 7 courses. We're going to have 7 different meals. So 1, 2, 3, 4, 5, 6, 7. For the first course, there are 7 choices. We don't know which container we have. We might get the salad. We might get the dessert. There's 7. One of them gets taken up, so now there are 6 choices for the next spot. And 5 choices. And then 4 choices. And 3 choices, 2 choice, and finally a single choice. Now, these are dependent because one depends on the other. So, multiply all of these together and you should end up with 5,040 different choices. Now, this actual number 2 is leading into our notes for today and talking about something called factorials. So, a factorial is when we take all of the sample spaces and we multiply them together. So it includes every number all the way down till 1. Factorial symbol is a little exclamation point. So now we're going to do n exclamation point. And just looking at it in mathematical terms, it's going to be n times n minus 1 times n minus 2 times n minus 3 times ... all the way down till we get to the numbers like 3, 2, and 1. Okay, so now coming back up here to this example, I'm doing it in red. What we did is 7 factorial. That is 7 times 6 times 5 times 4 times 3 times 2 times 1. That is what a factorial is, and that is what this formula is trying to explain. So you can read through the calculator notes on where to find that factorial on your calculator. So what is this leading into? This is leading into something that we're going to call permutations. And a permutation is basically an event when the order of the event matters, we're going to call these types of problems permutations. Okay, so here's something important. A linear permutation is an object in linear order. So a permutation, its formula, let's just put that in the box, is capital P parenthesis n comma r, end of parenthesis, and how that, or what that formula does is it takes n factorial and it divides it by, in a parenthesis, n minus r factorial. Okay, so let's do a little discussing of what n is. N is going to be your total number of choices. Number choices. R is going to be the wanted choices. I only wanted things with white or pink or something. So those are your wanted choices. Okay, so again, look at the calculator directions. You can look at those and you can find out where the permutation key is on your calculator, and you plug that in to your calculator. So let's actually take an example and show you what a permutation is. So for this first example, it says, how many ways can 3 books be placed on a shelf from 8 different books? Order matters. There is place 1, there is place 2, there is place 3. Now, if you think about what we did yesterday, we did, hey, this is 8 times 7 times 6. It works for some of these, not all of them. This is the permutation. I had 8 total choices. There's my total choices. And how many did I want to do something with? 3. So I would be plugging into my calculator 8, choose 3. Now, I just want to show you, at least on this one, mathematically what that says. It means 8 factorial is going to be divided by 8 minus 3 factorial. Okay, so that means the number 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is going to be divided, 8 minus 3 is 5. 5 times 4 times 3 times 2 times 1. Hey, look at everything that cancels out. Do you see that this actually equals 8 times 7 times 6? Is that what we did here at the beginning? This permutation, for certain permutations, this works. For others, it won't. So I just wanted to at least show you how it's kind of related to what we did yesterday. Okay, so on to the next example. For this next example, it says I have a committee of 18 people. How many ways can I get a president, a vice president, and a treasurer? There is a exact position. I'm just not being put on a committee. I want to be president. There's a reward for being president. I get to boss everyone else around. So if you wanted to think of it as a permutation, this is the permutation 18, choose 3 specific spots. And if you do that on your calculator, it should come out to be 4,896. Okay, now if some of you are thinking, oh, there's 18 spots for the first choice, and there's 17 spots for the second choice, and there's 16 spots for the third choice, guess what? Gave you the same answer. Permutation, but this is calculator, and if I had 15 choices, I don't think I'd want to do this. So I'm trying to show you, you need to be looking at your calculator for this stuff. Okay, so now let's take a look at this last example. How many different 4-digit garage codes can be made if there are no repeats permitted? Okay, so garage codes. Garage codes use digits. We have the digits 0 through 9, which actually means there are 10 digits that we can use. That's why we use the decimal or the decimal system. We have those 10. That's how we count. So 10 digits. I know that for the permutation, that means I have 10 digits and none of them are going to repeat. And I'm picking, oops, not 3, 4 this time. So that would be the permutation 10, choose, that's a really messy 4. 4, which is 5,040 for an answer. Again, that would be 10 for the first spot times 9 choices for the second spot times 8 choices for the third spot times 7 choices for the fourth spot. Again, old-fashioned way, need to learn how to do it on my calculator. Okay, so now we're going to go on and, we're going to take a look at the number of permutations when order matters, when P are alike and Q are alike and there's repetition. Okay, so keyword in here that we need to know, repetition allowed. Okay, it's going to change a little bit. So notice the number of permutations of n objects where there's P that are alike and Q that are alike. So the first thing I want you to get is however many P's plus however many Q's, that equals the n. And the formula says n factorial all over P factorial times Q factorial. Okay, that's the new formula. And now watch this different type of example. There are 3 identical white flags and 5 identical blue flags that are used to send signals. All 8 are to be used. That's my total number of choices. Total number of choices. Okay. Oops, let's finish that word. Choices. All 8 are to be used to arrange in a row. How many signals are given? Okay, here's the bad thing. If I wanted to do, 8, 7, 6, 5, 4, 3, 2, 1, which color comes first? The white or the blue? You can't do this. This can't be done this way. Okay? So, don't do it that way. X, yuck. Sorry that I made a mess. So here is what we're going to be talking about. There are 8 total choices. That's n factorial. N factorial, 8 factorial. Divided by, I have 3 identical white ones, 3 factorial, and 5 identical blue ones, 5 factorial, and that would be my P factorial and my Q factorial. So this, if you work it out on your calculator, should come out to be 56. I want you to do that. This is how we work if there's repetition in our objects. So repeat in objects. Now, one of my favorite types of problems to do when I have repeat in the objects is words and finding the probability of making new words. So how many ways can we arrange the word farewell? First of all, 1, 2, 3, 4, 5, 6, 7, 8. I know my n value is 8 here. So now I look, do you see how there's an E and an E? One of my repeat numbers happens twice, so that's a 2 factorial. Those are my E's. The next thing I look at, do you see how there's L's in here that repeat too? 2 factorial is my L's. Everything else is a single letter. So how am I going to solve this? Total number, 8 factorial, divided by the repeats, 2 factorial, and 2 factorial. And when you work that out, there should be 10,080 words that I could make. I shouldn't say words, arrangements out of the word farewell. So now let's take a look at the word Illini. 1, 2, 3, 4, 5, 6. So my n value is going to be 6. I look for repeats. I. So the I repeats 3 times. So think of that as 3 factorial. The L and the L, it repeats twice. So that's 2 factorial. So my equation is going to be 6 factorial divided by 3 factorial and 2 factorial. And if a letter doesn't repeat, we don't worry about it being in the bottom. It would be 1 factorial, which is just 1. Okay, so now let's take a look at the last word. The last word's collection. Hey guys, I know you can count. The n value is 10. So what letters repeat? The C's repeat. So my C value is going to be 2 factorial. The O's repeat, 1 and 2. So for the O's, that's a 2 factorial. The L's repeat. For the L's, that's going to be 2 factorial. Okay, so put it together now. 10 factorial, total number over all of the repeats. 2 factorial times 2 factorial times 2 factorial. Hope you found that factorial key on your calculator. It's going to be handy. This turns out to be 453,600 combinations or arrangements of the word collections. Okay, so now I would like you to try, turn off the video, try letter A, try letter B, and the rest of them, and then turn the video back on and see if you did those correctly. So stop the video. Okay, so welcome back. For the You Try It's, how many different ways can 2 geometry books, 4 geography books, 5 history books, and 3 different physics books, and notice they say different hooked onto it. It's not like what we did up here. So let's talk about this. Can be arranged on a shelf by subject. So the first subject that we're going to put on here is geo. So for geometry, I have a permutation 4, and I'm putting all 4 of them on that. So now I'm going to look at geography. And for the geography, I see that it's a permutation of 4, and I'm going to put all 4 of them on the shelf. So then I'm looking at history. And for history, I have 5 of them, and I'm picking 5. And Mrs. Kendall's got to go back and make a correction on hers before she works it out. For the geometry, I don't have 4 of them. How many do I have? Nobody said anything. How can you let me do this wrong? 2, pick 2. And then the geography was 4, pick 4. And the history is 5, pick 5. And then the physics is going to be, so for the physics, it's going to be the permutation 3, pick 3. Now, I wish this was it, but who said that geometry had to come first and then geography? I could change these different colors in another order too. So there's also one final one that we're going to multiply, and that's going to be the categories. So for the categories, there are 4 different categories, and I'm putting all 4 of those categories on here. So this is dealing with the order of the subject. So this is for the subject, and within each subject, here takes care of the physics. And you multiply that all together, and there are 829,440 different ways to put those books on a shelf. Never dreamed that many, but it works that way. Now, please note that these were all different. So now look at how this next one is worded. How many ways can 2 geometry, 4 geography, 5 history, and 3 physics books be arranged on a shelf? Not by subject. So they're not going to be grouped together in this way. So it's just the whole idea of, oh, how many total books do I have? My n value in this case would be 14. And then I have 2 geometry, that's 2 factorial, and 4 factorial, and 5 factorial, and 3 factorial. That's kind of like the word problem we did. So this is 14 factorial divided by my 2 factorial times my 4 factorial times my 5 factorial times my 3 factorial. And when you do that, you still get a lot. You get 2,522,520 different ways we could arrange them. So notice the category lessened it. When anything goes that a physics can beside a geography, beside a history, beside a geometry, you get a lot more. Okay, I hope you tried the back side too. So for the back side of this, we have letter C. How many different ways can the digits 755,232 be arranged? Okay, so how many total digits are there? There's n digits or 6 digits. There are 2 5s, so there's 2 factorial, and there's 2 2s, so that's another 2 factorial. 6 factorial divided by 2 factorial times 2 factorial, which is going to be 180. Okay, almost done. So we have a group of gems to design a bracelet, including 7 emeralds, 4 rubies, 3 diamonds. How many different bracelets are possible if each gem is unique? That means they're all different. So if they're all different, I have 14 objects. And it doesn't matter if I go emerald, emerald, ruby, diamond. I have 14 objects and they are kind of independent of each other. So that's going to be the permutation, 14 gems, and I can put all 14 of them beside each other. So that is a huge number of 87,178,291,200. Okay, there goes my phone. If you wanted to, you could have done 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. They're all unique. So you could have done that type of a method. Now, next one says how many if the type of gem is indistinguishable. That means every ruby looks alike. That means every emerald looks alike. So now, out of the 14 factorial, I have 7 emeralds. There are 7 things that repeat. It's kind of like the eyes in a line eye. And I have 4 rubies. So that's 4 factorial. And we're almost done. And this doesn't have to go. And then I have 3 diamonds for 3 factorial. And that would give me only 120,120 for my answer. So you got to read these carefully. You've got to watch as you're working on them. Take your time through the homework and make sure you check your answers online. I will see you guys on Monday.